Okay, let me introduce myself. I'm a developer advocate at Amazon Web Services. I helped AWS join the GraphQL Foundation last year, and I help represent AWS on the GraphQL Foundation. I'm a member of the GraphQL working group. Prior to joining AWS, I was a software engineer on the GraphQL team at Facebook. And then before that, I was a software engineer at Microsoft on the .NET Framework, Windows Server, and a bunch of other stuff. So here's my empowerment promise to you today. If you pay attention over the next 45 minutes, this is what you're going to learn. How does the GraphQL specification evolve? What are the principles that guide that evolution? What are the major proposals that we're currently discussing within the working group? And how might GraphQL look different if those proposals are accepted? And by the way, don't worry about taking pictures of any of these slides. I'll work with the organizers to make sure that the slide notes get sent out after the conference. This is a table of the different versions of the ANSI SQL specification. This is the specification for the structured query language. I hope many of you have used SQL before, because I'm going to be using it as an example for comparison today. You can notice that after the first version was released in 1986, it took about 13 years before they started adding any major functional changes to the language. And then after that, you see that the pace of additions started to accelerate, but even so, several years would pass before any major features are announced or added. And I want to compare GraphQL to SQL, not because I think GraphQL should evolve at the exact same pace at SQL. More, I just want you to see that there's bookends to how you want to evolve a specification. If SQL evolved too slowly, it would not be as relevant today as it is. And if SQL evolved too quickly and it kept adding new features, well, you would have a hard time knowing what features you can rely on, which implementations support which features, and which ones can give you the performance and the exact characteristics that you want. My point is that building a specification is challenging. Faster or more features is not always better. And I think SQL illustrates that. In that case, how do we navigate this set of requirements for evolving GraphQL? Well, there is a set of principles on the contribution guide for the GraphQL specification. And I want to go through these with you. The first principle is backward compatibility. Once you've written a query against an existing GraphQL server, future versions of the GraphQL specification and future implementations of that specification should not change the meaning of your query. Performance is a feature. This sounds kind of strange. Well, why wouldn't it be a feature, right? But what we're actually saying here is that with GraphQL, we specifically want to avoid syntax that can make it challenging to provide high-performance implementations for. And where you see this most obviously is in the GraphQL list. A lot of people, when they first encounter the GraphQL list, they wonder, how do I sort, group, join, and filter this list? Why aren't these operations available out of the box? Let's say, by contrast, OData supports link-like semantics on lists. Where is that for GraphQL? The closest thing we have is the connection cursor specification, which is a companion specification and not the official GraphQL specification. And the reason why it's not part of this is because we cannot guarantee high performance in all cases if we were to enforce that at the schema level. We also favor no change. And there's a good reason for this, because GraphQL as a specification needs to be implemented across dozens of languages and maintained by hundreds of individual contributors. So the bar needs to be very high in order for a change to be considered and accepted into the GraphQL specification. We also want to make sure that all of the new features that are accepted into the specification are adding something fundamentally new, and they're driven by real-world use cases. They cannot be hypothetical, theoretical use cases that would be a nice to have because it's a fun problem to think about. And they have to enable new capabilities in that it's not just another way to accomplish the same thing or a slightly more terse way to accomplish the same thing. And speaking of terseness, we also prefer a number of simple composable concepts. And we want to be able to assemble those concepts in order to express more complicated ones. And finally, second to last, we have preserve option value. This is basically where we want to avoid over-specifying. And where you see this is the lack of mention of the transport layer in the GraphQL specification. Because if we tie the specification down in terms of what the transport must do at the TCP layer, at the UDP layer, at the HTTP layer, we're not actually gaining anything. But we are invalidating or adding a lot more constraints into the implementation. And finally, we want to make sure that the specification is a human-readable documentation. It's a living documentation. We want to make it as understandable as possible. OK, so how exactly does GraphQL evolve then? It evolves primarily through the body known as the working group. This is a group of individuals who gathers on a monthly basis, and they propose and review major changes to the specification, RFCs, other proposals, and what have you. And anybody can join the GraphQL working group. Next, there's another body called the Technical Steering Committee. And the purpose of the Technical Steering Committee is to define the meta process. Why is it that the GraphQL working group is the body that governs the spec evolution? What about the different RFC stages? What happens if there is an impasse and the working group cannot figure out how to proceed with an RFC, which, by the way, has never happened. But these are the questions that the Technical Steering Group is chartered to solve. I mentioned RFCs. These can be submitted by anyone, and they can be championed by anyone. They go through 4 stages, which I'll show you shortly. And GraphQL also evolves in a less structured way via experimentation using the directives mechanic. And a lot of GraphQL server implementers and frameworks use directives to add all sorts of cool features to GraphQL without having to go through this formal process. And then we also have companion specifications. The best known of these is the GraphQL cursor connection specification. And we'll take a look at that shortly as well. Here's the RFC process. There are 4 stages. At stage 0, this is the straw man stage. And the purpose here is to knock the proposal down. We only want strong proposals to make it through the pipeline. And at this point, our purpose is to attack the proposal so that we can eliminate it if it's not providing any value. At stage 1, this is the proposal stage. And at this stage, the RFC now has a champion, which is somebody who's willing to do the hard work to guide the RFC through the rest of the process. We also need a clear explanation of the problem with illustrative examples, perhaps some provisional text spec edits, and we also need to identify some of the major challenges and the solution space. At stage 2, the draft stage, we have a consensus of what the preferred solution is. We've addressed all of the outstanding corner cases. We've selected one particular solution that there is consensus from the working group on. We have specific text edits. And then we also have a compliant implementation in the reference implementation that is GraphQL.js. And then finally, we have stage 3, which is something of a formality. At this stage, there's consensus that the solution is complete, that the spec edits are final, all edge cases are handled and documented, and that there's a compliant implementation in GraphQL.js with full test coverage. And at that point, an editor will merge this RFC into the specs master branch. Actually, Yvonne's sitting right there, so if you have questions about the next release, you can pick his brain. So there are about a dozen recently accepted RFCs. I'm not going to go through all of them. Some of them are fairly niche, like the greedy Lexer clarification. And this URL at the end, you can use that to go and read up more on these RFCs. Because I've actually pulled out the major proposals that I want to talk about today. Okay, and they are intermediate interfaces, custom scalar specification, defer and stream, input unions, and the HTTP specification. For each of these RFCs, I'm going to try and tell the problem discovery story. What motivated this RFC in the first place? Who is championing the proposal? What are the potential solutions that we considered? What is the preferred solution? Why do we need to specify this at all? Why couldn't we just use directives? And what does GraphQL look like after this change? And then there's also going to be a summary slide with current status, links, and related reading for each of these. Okay? First up, intermediate interfaces. Suppose we're building a schema to model a zoological survey. We might define an animal interface that has two fields, ID and name, and we might have various types in the schema that implement this interface, such as rhino and ant. And we can further extend these interfaces and types. For example, if we want to model the relationship between an animal and its descendants, we can have the children field, and for animal, the children is a list of animals. For rhino, it's a list of rhino. For ant, it's a list of ant. But wait a second. How many children does an ant have? Anybody know the answer? I had to look this up. The African driver queen ant produces 3 to 4 million eggs a month. So if we have a children field that just returns a flat list of millions and millions of children, probably going to be pretty challenging to build in a performant way. But we know how to fix this, right? Connections. Does this schema look familiar? How many people have seen the connection, the GraphQL connection specification? Right? Show of hands. Okay, not that many. Let me take a quick moment to go over this. The basic idea is that GraphQL lists are not the way you access large sets of data in GraphQL. The reason why you don't do this is because what it's saying is here are all of the children of this particular queen ant. Not a good idea, right? When you're dealing with large data sets, when you're dealing with web scale projects, you need to be able to paginate through that list. You need to be able to slide a window along a large collection, and you need to be able to pick up that window where you left off at an arbitrary point. So there's two general approaches to pagination. One is called limit offset pagination, and the other is called cursor-based pagination. And connections is an implementation of cursor-based pagination. And you can kind of tell what's going on here by just taking a look at the few lines of code that we have. Actually, the lower right interface is the most important one. This is the connection interface. And the connection interface says, hey, look, there's a bunch of edges, but this is not the full collection. This is just part of the collection. What part of it? Well, that's defined by the page info. The page info tells you where you're starting, where you're stopping by cursor, and then it's telling you whether or not there's a previous page or a next page. And then what about these edges? Well, each edge has a node field, which is the actual item itself. It has a cursor to describe how to pick up and end at that particular item inside this large virtual list. And then, of course, the node itself has this ID, this globally unique identifier. Or maybe not globally unique. There's no enforcement of that here. OK. But those astute among you might be wondering, how exactly do we express connections of different types? Well, we could try and do something like this. We could have this animal edge implement the edge interface, in which case the node is an animal. We can extend the animal interface with its children being an animal connection, and then we can have animal connection implement the connection interface. But there's a problem here, because animal edge.node is not actually valid. Because there's no way to tell GraphQL that animal is also an edge. This is the offending line right here. And there's another problem. There's no way to tell GraphQL that the rhino connection is an implementation of the animal connection. The fundamental problem here is that GraphQL has no way to specify an intermediate interface. And this is what led Mike Marcacci to champion the intermediate interface RFC. He considered a few potential solutions. And the way that you actually solve this in a lot of popular programming languages is through a mechanism called generics. Anybody who's written Java or C# or C++ has seen these, right? You can have a list of type string. You can have an array of type int. Those languages would probably build this using the generic mechanism where they have something like connection of type rhino. But there's no way to express this in GraphQL. And actually, if you think about what it would take to evolve the GraphQL language to express generics, it's a tall order. And so Mike pivoted to using intermediate interfaces as a pragmatic way to solve this problem. Here's the proposed solution, according to Mike. you have something like the type Rhino edge implementing animal edge and edge. Notice the syntax here, right? And notice that you must specify the entire set of interfaces. So unlike Java, you don't get the hierarchy transitively. Now you might wonder, well, why do we need to specify this? There's two major reasons. The first is that directives are simply insufficient to express this kind of problem. Maybe, if you're a directive ninja, you can build something that roughly approximates this, but I doubt it. The second change that needs to happen is that the introspection query for when you fetch the type for field, that interface now needs to return a list of interfaces instead of a single interface. And actually, this proposal has already, this RFC has already been accepted, and so this should be shipping very soon. Here's some links. There's also, the last one is very interesting. This is a post by Andy Merrick, the maintainer of GraphQL Java. And he actually talks about the fact that this explicit interface declaration allows a very interesting, it gives you a very interesting tool for refactoring GraphQL schemas. I highly recommend taking a look at the third link here. Okay. The next RFC I want to talk about began with the problem of modeling time in GraphQL. See, GraphQL only has 5 built-in scalars: int, float, string, bool, and ID. Every other scalar needs to be added as a custom scalar. And so one of the first problems that GraphQL developers encounter is the inability to model time out of the box. So they go to the docs and they see, okay, well, I need a custom scalar. So they start building a custom scalar. And after a couple days of that, they go, wait a minute, I can't be the only person to have hit this problem. So they go looking around online for solutions. And if you go looking around online for solutions, this is what you'll find: popular packages that support the datetime scalar. The top one is GraphQL ISO date. This is an NPM package, and I know the text is a little bit small, but it says that this is an ISO date that implements the RFC 3339 specification. The RFC 3339 specification is a specification that defines some of the standardizations of date time. And then GraphQL Java Extended Scalars does the same thing. Now suppose that we built 2 GraphQL servers, one in Node and one in Java, that use these 2 popular packages respectively. And I try to store a date with the input value here. Node is going to strip the time zone offset, whereas Java will maintain it. And if I store these 2 values to the database, I have 2 very different times. Not good. If I have a time that goes down to the nanosecond and I try to store these, Node will strip the nanoseconds. Java will maintain it. Less of a problem, but depends on your use case, right? So my point here is that it's not that the Java implementation is better or that it's more correct. It's actually that both of these implementations say that they implement RFC 3339, but RFC 3339 is not actually a complete specification. There are corner cases that RFC 3339 doesn't talk about. And not only that, RFC 3339 is actually it's considered a profile of another datetime specification called ISO 8601. Okay? Why am I telling you all this? Because I'm sure you're going to forget those ISO, RFC, whatever immediately, unless you're a datetime nerd. But you're going to forget these because this problem, when you walk up to it, it seems simple. Why isn't there a datetime? Right? Why isn't there a datetime? But when you dig into it, you start to realize the incredible amount of complexity there is around trying to standardize something as widely used as datetime. And the evolution of this particular RFC is particularly interesting because that was Andy's initial idea. He had that question: why can't we just add datetime to GraphQL? It should be in there. Nobody should have to build this. And this is the rabbit hole we ended up in. RFC 3339, ISO 8601. You can go read the RFC for the original datetime scalar proposal. It's very interesting. But anyway, the reason why we can't do that is because if we if we include RFC 3339 datetime, why wouldn't we include ISO 8601 datetime? And those are not the only two datetime specifications. There are more out there. So if we started adding those, we'd have something like 3 or 4 datetime scalars next to the 5 built-in scalars. Almost half of the scalars in GraphQL are all about datetime. And that's just datetime. Why do we have to give datetime any special treatment? What about URL? What about email address? What about latitude and longitude? Right? That basically, if we went down this slope, the GraphQL working group would do nothing but spend time reviewing these proposals for including new custom scalars, because everybody wants their scalar to be included so that they don't have to build it themselves. What the champions, Evan and Andreas, ultimately ended up doing is pivoting to describing a mechanism for expressing the custom scalar instead of adding the custom scalar itself. So let's try and restate the problem. The problem is that tools cannot distinguish between multiple formats of a custom scalar. And even if you choose one format like RFC 3339, there's ambiguity for serialization and deserialization. Now, what are some potential solutions for this problem? As I said, the first one, the most obvious one, is to just add more custom scalars. I talked about why that's problematic. But the other one we could do is we could describe the custom scalar in the description. For example, we can copy-paste the RFC 3339 spec into the description field for our custom scalar for datetime. Maybe, I mean, that's a lot of text for the description field. I don't know if anybody's going to read that once we paste it in there. So instead of pasting it, maybe we reference it. Maybe we reference the URL for RFC 3339, and we say, this is my best effort implementation of RFC 3339. We could introduce a brand new grammar for describing these specification URLs, or we could introduce a standard directive to reference a spec URL. And the solution that the champions settled on is to use a standard directive to reference a spec URI. And you can see this in an example here. We have the scalar datetime, and then it's followed by the special directive at specified by. And it takes a URL, and it says, this is the URL for RFC 3339. This is what this datetime, this is the specification describing the behavior of this particular datetime custom scalar. But I mentioned that RFC 3339 is not complete. What if we add some corner case handling on top of RFC 3339, and I have a slightly different implementation, right? Well, then I might want to host it at a different URL, and you can do that. You just change the URL out. And there's even some discussion of potentially hosting something on GraphQL.org, like GraphQL.org/scalars, and this is where we have something like the GraphQL datetime. And if you go to that URL, you might find something that says, well, this is based on RFC 3339, but this is how we handle the following edge cases. Why did this need to be part of the specification? Well, we're effectively reserving the at specified by directive to mean exactly one thing. And nobody else in the future is going to be able to take this directive and have it mean something else. We also need to be able to return directives from the introspection query, because without that capability, there's no way to make sure that the tools match up. So for example, if I want to choose a datetime structure that matches the datetime picker in Android, I want to make sure that it's going to serialize correctly. And the only way to do that is if I can have tooling that says, oh yeah, this is a compliant implementation that matches all of the client-side implementations. And this RFC is now in stage 2. Here's some links. Okay. Suppose that you're building an application with a classic REST API. And when the app starts up, you perform the authentication request to validate the user, and then you send out a bunch of REST API calls, just like what Tanmai showed you in his talk. Now these REST API calls are going out on the network in parallel, and they come back at different times. You don't necessarily have control over when those responses come back onto the client. But as each response comes back to the client, you can make a decision. Did I receive enough data to begin interacting with the user? Right? And you can make the decision, ideally, maybe even after only the first request comes back. It has to be the correct request, of course. But you can do that nonetheless without waiting for all of the initial REST API calls to complete. However, if you used a GraphQL endpoint instead, and you collapsed all those REST API calls into one network request response round trip, then the response is actually, the latency of that response is equal to the latency of the slowest field inside that GraphQL query. And you don't have much control over this request-response interaction anymore, right? You have to wait for the slowest thing. It's almost as if GraphQL is forcing you to make a trade-off between this nice single request-response semantic versus the ability to prioritize some payloads over others. Let's take a look at an example. So here we have a query that fetches a viewer. It fetches the viewer's first 20 friends, and for each friend it fetches the ID. And then below it also fetches this group admin fragment. And let's suppose for a moment that the group admin fragment is not critical. I can start displaying my app interaction. I can start rendering my UI before this group admin fragment makes it back. And it's also particularly slow to run. So that means that in order to render the friends, I have to wait for the group admin fragment to resolve. So this is going to create a suboptimal user experience because I'm basically blocked on the slowest field. And as for the first 20 friends, maybe I don't even need to display 20 friends. Maybe I can get away with displaying the first 4 or 5. And I can stream the rest in. So we see that there are actually 2 problems here. One is that certain parts of the query are more important than other parts of the query. And 2, for collections, the first few items in a collection are more important than the remainder. So to describe these 2 problems, the terminology here for the first problem is defer, and the second problem for delaying fetching more items in a list is called stream. And that was the genesis of the stream and defer RFC. This is being championed by Liliana, Kawei, and Jennifer. This is a distilled problem statement. With defer, what we're trying to do is we're trying to allow the client to render faster parts of the query without waiting for slower fields. And for stream, we're trying to render the first few entries in a collection without waiting for the entire set. Here are some potential solutions. We don't actually need these mechanics, strictly speaking, right? Because just as we collapse all those REST API calls into one network request, we can also unbundle that GraphQL request into multiple queries. But by splitting the queries, we have a couple of trade-offs. First is that we've still increased the latency because we're issuing 2 queries side by side. And especially if you're using a device, an embedded device, or an older mobile device, that's still congestion of the limited resource of the network. The second is that on the back end, it's also going to take more work, right? By processing 2 independent requests, those requests might be routed to different shards. Each server has to perform authentication and validation on its own again. And it's just doubling up the amount of work because there's quite a bit of overhead for each request. And finally, the client also needs to know which fields are fast and which fields are slow in order to know how to split the query exactly. Another potential solution is called prefetching. And this is an interesting solution because instead of waiting for the client to make a request, the server pushes data to the client when the client's network is idle. Now, this is a pretty crazy solution because the server, how does the server know what data to push to the client? It's guessing what the client is going to need, right? If, let's say, the server just pushed a massive payload, and then a second after that, the user shuts down the app and uninstalls it. That's complete overfetching. That data was never useful, right? And that can always happen. So with prefetching, there is always the potential for overfetching. And in order to reduce the amount of overfetching involved, you have to have really good predictive algorithms. Suffice to say that prefetching is a very tricky solution. And finally, we have a solution where we send a single request, but instead of getting a single response, we get a multi-part response, or chunks of a response. And this has also a bunch of trade-offs. So the first is that we now need to have the ability to specify priority inside the query itself. And second, we need a transport that is able to send in the response in different parts. But this is the solution that the champions are proposing. And here's what it might look like. We basically have the query, and we've decorated this query with these two new directives, stream and defer. And with stream here, I hope stream, they're both kind of intuitive. Stream is saying, you know what? I want this collection, but the first element in the collection is more important than the rest. Give me that first if you can. And with the defer directive, we're saying that this entire group admin fragment is less important than the rest of the query. Give that to me whenever you can. So here's an example. Instead of getting a single JSON document in response to this query, we might get the response in several parts. We might have one patch that comes in that says the viewer friends/one path contains the ID 4. This is the first friend's ID. The second viewer friend is ID 5, and on and on. I'm not going to do all 20. And then later on, this defer fragment came in, where it says the viewers, so the name is a little bit different here, but managed groups, group admin fragment. And then it also has this extension down here, which is final equals true, which says this is the last chunk of the response. No more will follow. And by the way, if you're wondering about how this works at the transport level, you can use a mechanism like HTTP chunked encoding. So here it is. These are the building blocks of this proposed solution. Now, why do we need to specify this? Well, again, we need to have the @stream and @defer directives mean something specific now. We don't want anybody commandeering those directives in order to mean something else. The second is that we do need to say that the transport has to have some notion of this. While I mentioned earlier that we prefer option value, we don't like to specify anything in the transport layer, we do have to describe some of the minimum functional capabilities at the transport layer, or else this whole thing is not, it's going to collapse into the old implementation. And then finally, we have to have those mechanisms like path and isFinal to describe how exactly we're patching the incremental data structure that's being received on the client. And this proposal is currently in stage 1. By the way, one of the things that makes me really excited about this proposal is not even in the RFC. It's the ability to model a mutation that that models an asynchronous request. So let's say you have a mutation where you make a credit card payment. And the API can acknowledge that it received this request, but it's probably not going to process the payment itself. It's probably going to use some other backend provider like Stripe or Square or something, and it's going to process the payment through that, right? So as it does that, I don't want to know about the underlying details, and I don't want this mutation to just sit there for 10 seconds while this process is being run on my behalf. I want to get an acknowledgement immediately after I send the mutation, and then after that payment is complete, I want to get the deferred result. Because the current way that you do this is that you issue a mutation, and the mutation completes immediately, and then you issue a subscription to subscribe to the result of that mutation, which is a lot more annoying to deal with. And not only is it more code, but it's also susceptible to race conditions. So I think this would be a much better solution, and I'm excited to see if we can take defer and stream in this direction. So here's some links you can use to read up on the status of defer and stream. And by the way, and this is, you don't have deja vu. You've seen this defer and stream before. Actually, we've talked about it as far back as 2016. So this, again, goes back to this idea that we want to make sure that we're evolving the specification in a thoughtful way, and we're not rushing into anything. All right, input unions. This is another classic. This one has also been around almost since the beginning of GraphQL. Input unions. How many people have heard of input unions? Okay, a couple people. All right, but most people, this is going to be brand new to you. A lot of new GraphQL users, when they start off with GraphQL, they run into this interesting bit of trivia that the GraphQL input type and the object type are two different types. And they wonder, well, why can't I just specify an input? Why isn't the input type just an object type? And one of the reasons is because object types can be, when they're returned as fields, the fields can return unions. So it can return one type or another type. Ooh. I'm getting too excited there. It can return one of multiple types. And then you can have a fragment that specifies that you're selecting fields onto a certain type. And this is a very useful mechanism, this input unions, union types. But this feature is not available for inputs. Let's take a look at why you might want it. Let's say we're building a pet store, and we have this mutation to add a pet. But this pet store has multiple different kinds of pets. And so you know, if you're from an object-oriented background, you know if that there was some sort of abstract base type called pet, it would make no sense to add a pet because you don't know what that is. Right? And adding a pet by itself is not sufficient information. You need to ask what kind of pet it is. So there's a solution to this, which is to use one mutation per type. Let's say that our pet store has 3 different kinds of pets, cats, dogs, and rats. It has one mutation for each of these, add cat, add dog, add rat, and each of these takes the corresponding input type. Okay? And actually, this is the solution that Facebook uses. Now, you can see that one of the problems with this is that the schema becomes bloated, and that you have all sorts of different mutations that do roughly the same thing. So there's another approach to this, which is called tagged unions. And the way that the tagged union works is that instead of having one mutation for each type of pet, you have a single mutation, and that single mutation takes as input a pet input. And the pet input has tags for each of the different possible animal types, cat, dog, rat, etc. And the problem with tagged unions in GraphQL is that it's very easy to have nonsensical inputs because the tagged union is going to have each one of these tagged fields, it's going to specify each one of these tagged fields as optional. Right? So if it specifies cat, dog, and rat all as optional, that means that a pet input with none of them is considered a valid pet input. But that clearly makes no sense. How do you add essentially a null input? It makes no sense. Right? Sure, you can handle that with a useful error message, but it still is not communicating the constraints of the contract. And the other way that pet inputs can become nonsensical is that because they're optional, you can define all of them. So in this case, I've defined a cat and a dog. What does this mean? Am I trying to add 2 different pets in a single transaction? Did I make a mistake? Am I creating some sort of weird cat-dog hybrid? It's ambiguous, right? What you really want is input unions, true input unions. And what this is what we're saying is, excuse my bastardization of the schema description language, but we have add pet here, and pet input is one of cat input, dog input, or rat input. This would be kind of nice. And then we would be able to write the mutation down below as follows. Add a pet, and then the pet input just takes the parameters. I want to add a pet named James, and its age is 1. But can anybody spot the problem here? Yeah, the type, right, yeah, exactly. What type of animal is James? It's unclear. And so that's what brings us to the input union specification as we know it today. This is being championed by Benji and Lee. And we've seen the 2 common workarounds, tagged unions and 1 mutation per type. So just to summarize, the problem here is that we don't have the ability to specify polymorphic inputs. And the workarounds result in either a bloated schema or they result in an unclear contract. But going back here, we said that this is not actually going to, this is introducing a different problem. I don't know what type this animal is. I need some sort of discriminator. And that's where the debate about input unions is currently at. So there's a bunch of potential solutions for solving this discriminator problem. For example, we can pass in a type name field. We can pass in a configurable field. We can discriminate by order. And I'm not going to talk about the rest. You can look these up. It gets pretty deep. But I just want to show you very quickly. This is the solution that Benji favors. And by the way, he did a fantastic job of creating an objective set of criteria to evaluate all these 5 different approaches for discriminators. Definitely go take the time and read just to see how he did this, because it's fascinating. And this is where we have somewhere in the spec that says, well, the input union of animal input is defined, it's discriminated by with a field called kind. And that the kind must be either cat input or dog input. And then notice that you can specify the cat input, and now this mutation is unambiguous. This is saying that James is a cat, right? Interestingly, Lee is championing the order-based discriminator, which is a different proposal, which just says that instead of having any sort of discriminator inside the structure, James is whatever those two fields match first. Pretty interesting, right? So we basically scan down this list and we say, name and age. Can that satisfy the cat input? No. We move on to the dog input. No. Can it satisfy the rat input? Yes. James is a rat. So it's a very interesting approach. And you might think it's kind of silly, but if you actually look at the use cases, if you try to build one of these out, you may find that your mutation, your input unions for your mutation are unique enough where this is not actually a real problem. And this is certainly simpler to implement because it doesn't require any significant changes to the language. Input unions is currently at stage 2. Here's the RFC. Okay, I am running out of time, so I apologize. I have to go a little bit faster. But the final proposal here is the HTTP specification. And the genesis for this is, let's say I tell you that I have a GraphQL server at api.com/GraphQL. Make a request. How do you do it? And let's say you put this you put this into GraphiQL, and you get nothing because I've disabled GraphiQL. I've disabled introspection. How are you going to do it? You know it's HTTP. Well, here's some questions you might have. Is it using any sort of further path or subdomain for accessing this API? How do the operations match onto HTTP verbs? For example, can I pass everything in as query parameters inside the get operation? Does everything have to go through the post? What if I'm running in an enterprise firewall that disallows post? Does everything have to funnel through get? And again, variables can also be defined. If you're using a post request, you can put those into the body, but if you're using a get request, there's no body. So lots of questions around this. And it's interesting because most of the HTTP interactions for GraphQL are kind of done by example. It's basically whatever worked before. And that's why this specification is being championed by Sam and Yvonne. And the problem, again, stated like so, is HTTP is the most popular GraphQL protocol, but how exactly you interact with it is loosely defined. It's actually defined by precedence. There's no docs that really spell it out for you. And that means that tools cannot anticipate how a GraphQL HTTP endpoint is going to actually behave. And this is partly by design. I mentioned before that the spec has avoided talking about things like TCP or UDP. It's certainly going to avoid talking about HTTP. And in fact, it would be overly restrictive even for Facebook's use case, because at Facebook, while HTTP was used as the transport layer for GraphQL requests coming from mobile and web clients, internally, servers could communicate with the GraphQL API via Thrift. So that's another protocol altogether, right? And I mention this because if we had specified HTTP, well, does that mean we have to specify what happens with Thrift? What about gRPC? So again, you see that the reason why we left it out is because there's no value in going down that slippery slope. So here are some potential solutions. One is that we can just reach out to the major implementers and ask them to implement a certain standard, and then that just becomes a more, how shall I say it, a more cohesive set of standards. The second is that we could have put this into the official HTTP specification, the official GraphQL specification. I just talked about why we might not want to do that. The third one is an idea that I've been toying around with for a while, which is that we could run some sort of feature query. So imagine that we can run the introspection query, and then the GraphQL server can return a bunch of URIs that says, I also extend the base implementation with the following extensions. So this could give you a hint of what transport it's using for GraphQL subscriptions, how it's handling HTTP interactions, whether it supports live queries, and on, right? But the solution we ended up with, was to use a companion specification similar to the cursor connection specification. And why specify this? Again, directives are just incapable of expressing this thing. And this is not an RFC. This is a companion specification. So the RFC stages don't apply. But this is one of the things that we want to examine as the technical steering committee. How exactly do we formalize a process around companion specifications? We have a couple of ideas, but it's really one of these things that we have to figure out soon. And then here are the links for HTTP. So that's where I'm going to end. I want you to consider joining the GraphQL working group. This is where you get a front row seat to all of this action. And in fact, we highly encourage participation and feedback in this process. GraphQL is unique in that it is one of the few open source projects that is so widely used, that is so well liked, and yet has so few barriers to participation. I also want you to take a look at the RFCs if any of these sounded interesting to you. They're all out there. They're very readable. The examples are great. All of the champions are doing a fantastic job. And then, of course, if you're concerned about all of this process, consider joining the GraphQL Foundation if you want to represent a company. Thank you very much.